Okay. Itamar told me that some of you are unhappy about, don't exactly follow the general framework that we have been pursuing in the last two classes or so. So I will try to explain again what is the question and what's the motivation, and what's the framework. So let's go back to the Hopfield model. Just write the connectivity matrix equal to 1 over n, sum over mu, pi mu, pj mu. Right? So one way of thinking about how such a matrix can emerge is by considering a learning rule that has the following form: 1 over n jij mu is equal to 1 over n pi mu pj mu. So whenever a pattern is presented to the network, the strength of connection between neuron I and neuron J change in accordance with this value 1 over n, the product of pre- and postsynaptic activities. Now let's consider this specific connection between neuron I and neuron J. So this is a connection between neuron I and neuron J. If for a particular pattern pi mu and pj mu have the same sign, then this the connection there would be potentiation. The connection would become stronger, and if they have opposite signs, then the strength of connection would become weaker. Another way of thinking about it is using the Markov chain framework. So we have many states. Let's say that this one would correspond to jij being equal to 0. This one would correspond to jij being equal to 1 over n. This one would correspond to jij is equal to 2 over n. This one would be jij is equal to -1 over n. And whenever a new memory is presented to the network, the state of the synapse changes in one direction or the other, depending on the value of the product of pre- and postsynaptic activities. Yes?
And so what are the circles?
Circles now. So if previously these two circles corresponded to the two neurons, now the different circles correspond to the different states of the synapse. The synapse itself can be thought of as a Markov chain. How many states does this Markov chain have? An infinite number of states in the Hopfield model. Because every new memory pattern can bring you either to the left or to the right, and if we don't restrict ourselves to a finite number of memory patterns, this can go on forever.
So can you explain again how did you come up with jij equals to 1 over n?
Well, let's start with jij being equal to 0.
Okay.
Now I add one pattern. The change in jij would be equal to either +1 over n or -1 over n. Okay? Okay. So in principle, thinking about it this way, we have a Markov chain, but it's an infinite Markov chain, which doesn't make much sense. Doesn't make much sense in both because synapses are bounded in biology, and because it doesn't make sense that the number of synapses would be infinite. So the number of states in a synapse would be infinite. Number of states should be finite. I don't know how many, maybe 100, maybe 50. There are various ways of thinking about it. The way that it's written in the Hopfield model, you can imagine that the number of the states are discrete, but the synapse is unbounded. You can imagine a normalization of a synapse, which would keep the synapse finite, but the difference between the states would go to 0 within the synapse. This would definitely be true if we can scale the temperature, if we imagine the case of beta which is infinite. So either way does make sense. So we should consider another model of a synapse that has a finite number of states. Let's say that it will end here. Let's say that there are 10 different states or 50 different states. But that's it. So thinking about it from a synapse point of view, at some point the synapse would reach the bound which it cannot pass, and then either it will get stuck, this is we consider the hard bound, or it will go back. This would be the case of elastic bound. But in any case, we should modify our model. And what we did in the last 2 classes or so, what we did was to consider the consequences. But this time we did not restrict ourselves to this particular model, but said something more general. We said that if you are in a state, in a particular state, you will either potentiate or depress with some probability. Now, the probability for potentiation and depression is the outcome of a particular learning rule that we are considering, and the realization, the particular assumption about realizations of memory patterns. So if we remain in the Hopfield model, assuming that this is a learning rule and the patterns are plus and minus 1 with the probability 1/2, this will result in a model in which you move up or down with the probability 1/2. If we consider a case where we're still in the Hopfield model, but this time Pi and Pj are 1 and minus 1 with a different probability, then this would be a model where there is a higher probability of moving to the right and a lower probability moving to the left, but still you cannot stay in the same place. A third possibility is to consider a model in which it's like the Hopfield model, but there is a change with some probability. It would be a third model, and then you move either to the right or to the left or you stay. And one can imagine many other models. Now, in all...
Where is this discretization that you just described the Hopfield model in a different way?
No, because there is a bound.
Only because of the bound?
Only because of the bound, yes. So if the bound is such that there are 50 states, then you can say that the discretization of a synapse is into 50 different states. And if you normalize a synapse to be, I don't know, between 0 and 1, then every step would be 1 over 50. You had a question? I heard a female voice saying something. Okay. Okay. So this was the motivation. And then we said, okay, fine. So let's, rather than thinking about readout and the entire network, let's consider a single synapse and see whether we can say something about the dynamics over time of a single synapse. Now the dynamics will be stochastic because memory patterns are stochastic. Maybe the rule has stochasticity in it, but this is what we did. And then we, thinking about the problem as the problem of a Markov chain, we immediately realized that the dynamics of a single synapse will converge to a stationary distribution. Now, the fact that it will converge to a stationary distribution independently of the initial condition. So we can think about learning of a particular pattern as an initial condition, but then it will converge to a stationary distribution. And the problem is that it will converge exponentially fast. It will converge exponentially fast to a stationary distribution. Fast with what? What are the units of time here? The units of time is the presentation of different memory patterns. So we expect that after presenting the network with not a large number of memory patterns, the single synapse will no longer remember or will no longer contain any information about a particular memory pattern. Now, if there is no information at the level of a single synapse, and memory is in the synapses, then we have a serious problem. Now, from here, it's only details. We know what we are interested in. We're basically interested in the subdominant eigenvalue of the transition matrix. We know that there will be one eigenvalue that will be equal to 1, and all other eigenvalues in general will be smaller than 1. And what we care about, if we want to know how much time or how many patterns can be added to the model before all patterns are lost, all we need to do is to compute this eigenvalue. Is it clear? Are there any questions? Okay. The next step was to say, okay, let's assume a particular model. This particular model was a model in which there is a probability of F minus for depression, probability of F plus for potentiation, and probability of 1 minus F plus minus F minus for staying in the same place. This was our model. Then we can write a transition matrix, and we consider two similar matrices that differed on what's going on in the boundaries. And then we need to take this matrix and compute its eigenvalues, or more precisely, the subdominant eigenvalue, the second largest eigenvalue. This is what we need to do. Now, the problem that we were discussing is more general. I mean, you can imagine that there is a different learning rule in which there is a probability of double potentiation or double depression. And then there will be a different transition matrix. But still, the memory will be determined by the value of the subdominant eigenvalue. Well, one is the largest one, so the second. The capacity or the number of patterns that can be stored before the synapse reverts to a stationary distribution will be determined by the eigenvalue of the new matrix, and there's no reason to think that this will solve the problem. Still, we thinking about it this way, we expect the memory to be lost after not a large number of memory patterns. Other questions? Okay, so we consider this particular model, and then I stated the value of I stated that the subdominant eigenvalue has a particular form, and then we took we considered the case of large M, a large number of internal patterns, and we found that the subdominant eigenvalue has this particular form. That's what we did. And looking at it this way, we note that if F plus and F minus are different, I'm sorry?
What is the number n?
Number of states.
Oh, you open
I give it m. M can be 50, or can be 10, or can be 100. This is just a parameter.
But you wanted it to be small, so why do you take the large?
Well, okay, that's a good question. Small or large compared to what? So it would be small. It's small compared to n, number of neurons in the network. So in the Hopfield model, the original Hopfield model, in principle, you would go from minus p over n to plus p over n. If p is order n, then basically you go from minus 1 to 1 to plus 1 in steps of 1 over n. So this would be an order n resolution. So here we are order m resolution, mem, where m can be large, but still much smaller than n. 50 is large for the cosine approximation. Okay?
Why didn't you look at the third eigenvalue?
Well, this is not the third in it. This is
Not the third in size.
not in the size. This will be the largest one. I'm just following the notations of Abbott and Fusi in the paper. I will post. This is in the supplementary of the paper. I will post it online. So one thing that you immediately notice is that if f plus and f minus are not equal, then if m is large, this would be the dominant term, 1 minus this term. So discretization will not help, basically. Doesn't matter if you're 50 or 100. This is the deviation is expected to be large. Now the way to think about it is, well, if f plus is different, let's say that f plus is larger than f minus, and you start in a different place, well, after on the order of f plus minus f minus time steps, you will reach the bound. Times m, you'll reach the bound. And then there will no longer be information about the question of whether you started from this point or started from this point. So the memory about the information about the memory pattern will be lost. Similarly, if f plus is smaller than f minus, then after number of time steps, which is proportional approximately to the difference, you will reach the other bound. And then you'll get stuck there, and then information will be lost. If f plus is equal to f minus, then in the space of states, the synapse will do something like a random walk in the state until it will reach the bound. And this will take a longer time. Because this will be a random walk in the state of the synapse. This will not be a biased random walk, as in the case where these are different. But still, eventually it will reach the bound. And when it will reach the bound, then information will be again lost. So the question is, thinking about it in this framework, the question about memory capacity is, how long will it take you to reach the bound?
In the bound, it's not lose all the information. Because if it was infinity, it was somewhere in the area of the bound.
Well, if you start from this point and reach the bound, and then there will be another potentiation, then you don't know about this potentiation.
You don't lose everything.
Well, you don't lose everything also because there are many synapses.
Yes.
So, but this would give you an order of magnitude.
No, you don't lose everything in this synapse. Because in the right side, not in the left side. It gives you some information.
It will give you some information, yes. But this is where the model differs from the Hopfield model. So in the Hopfield model, whenever you have potentiation or depression, you lose information because there's like an added noise to the state of the synapse. When you reach the bound, that's more serious because it's direction.
What you said about the random walk?
Yeah.
You said it about the case that f plus and f minus are equal or equal to half?
Equal.
Just that it's
enough that they are equal. So if they are equal, then this is equal to 0, and then the subdominant eigenvalue will be dominated by this term. Yes?
Where do you see here the association? I mean, do you see?
No, you don't. No. This is like what we started by saying that having information in the synapse, some information is a necessary but not sufficient condition. So there are two issues here. One is, well, maybe there will be some information about the memory pattern, but not a lot of information about the memory pattern. That's one thing, and maybe you will not be able to retrieve it by the dynamics, or association will be lost. Many additional things are necessary, but here we can think about it as a bound. So if all information is lost in the synapses, then surely there will be no association, there will be nothing.
But anyway, you will get there. So.
What do you mean anyway?
To the boundary.
Well, not after one step.
Yeah, but.
The question: how long?
How long do you want to keep the memory? I mean, what type of memory issue?
Well, I want to. I'm thinking about. I remember my late grandmother. I want to keep on remembering her for the rest of my life. That's a long time. Well, I hope.
But how can you control this? I mean, this doesn't seem to have infinite.
Well, I said a long time. I didn't say infinite. But still, in the Hopfield model is also limited. The Hopfield model is limited. We get something like order n, capacities order n memories. But here, the limitation will be much more severe. So we already saw something. We saw that in the Hopfield model, when potentiation and depression are not equal, then we run into catastrophes. You already see it here, in the more general case. So we can see here, we can understand also from this why we had a problem, or it's a different kind of, it's a related problem to the problem that we considered in the unbalanced Hopfield model.
Do you see anything like that this optimizes, I mean, the relation between the probabilities to get depression or potentiation?
In the biology?
Maybe, or in general. I mean, yeah.
There's no general, there's biology.
Yeah, I think, biology. I mean, is it something that you see that optimizes the
Okay, so the question is, what can we say about biological memories? Are they optimized? Are they optimal in any sense? So this is a question that has been partially addressed in beyond the theory. What people have argued, and people have argued this for the cortex and also for the cerebellum, that if you look at the distribution of synaptic efficacies, they follow a distribution that is predicted from models of optimality. This is a claim that you will find in the literature in the last decade. I don't believe it, but still people argue that this is the case. This is coming from a different framework, from a framework of optimal coding in perceptrons. This is something that you may do next year. With respect to balancing potentiation and depression, you see such a thing in the sense that if you look at distribution of efficacies, they are unimodal. Doesn't seem that they are at saturation. But it's more complicated. Let's say that I don't know. Okay, relation to biology, I don't know. But it's an interesting question. Yeah. There are claims in the literature. People like Sam Wang from Princeton, Carl Peterson had a was it PNAS paper like a decade ago, where people claim that in fact synapses are binary. They have just two states. This is a claim that some people believe. and that when we see these nice LTP curves, which look smooth and nice, the result is that the reason that they look this way is that you average over many synapses, each one moving from unpotentiated to potentiated state after a different number of repetitions. So on average, it looks graded, but in fact, at the level of individual synapses are binary.
But from what you learned about cubic neuron, you do see graded differences, like the number of the AMPA receptors, or
at the level, again, here there is a debate well, there has been a debate in the literature. I think that it's not resolved, but people stopped caring too much about it. And the debate is whether synapses, how many states do synapses have? That's one question. And how many, and another question that has been of a lot of interest in the last decade, people like Surya Ganguly, Stefano Fusi, Larry Abbott have addressed is how many internal states synapses. So the idea is that the synapse can have many internal states, and these internal states do not necessarily manifest as a change in synaptic weight, but they will change the transition probability. And there are some interesting ideas there, but we will not discuss them. Okay, so let's consider the case of the subdominant eigenvalue, which looks like 1 minus square root of f. Now we will consider the case of f plus being equal to f minus. This is an interesting case. So it will be 1 minus f, something like pi squared over m squared. So
Is this the lambda 3 or?
this would be the dominant, yes, the dominant eigenvalue. Yes.
Maybe I'm missing something, but if f plus and f minus are equal, shouldn't they be equal to half?
Probability of staying.
No, the probability is
Why should they be equal to half?
Is there a probability for the state to remain equal?
Well, you can imagine a model where you'll have a probability of not changing at a single sign. Okay, so there will be a signal which is kind of difficult to define, but we will not define it exactly because it's difficult. But still, we know that there is a signal. So let's assume that we have this model, and we are thinking about all these synapses, and there is a stationary distribution of values that a synapse can attain. And this stationary distribution can depend on, so this would be the value of a synapse, and this would be the probability or the number of synapses in the network that we'll find in different states. So this is an example where there are just 5 states. And so this is a stationary distribution. Of course, every synapse will be in a different state, but this will be the stationary distribution. Now, let's assume that the synapse is potentiated. Let's consider all the synapses in the network that were potentiated. In that case, the distribution will now have a slightly different shape. So there will be no synapses. This would be the potentiated ones, and this would be higher. And in the case of depressed ones, so this would be the depressed ones. So all synapses that were potentiated, the distribution of all synapses that were potentiated immediately after potentiation would look something like this. And the distribution of all synapses that were depressed would look something like this. So here there will be more, no, sorry. Other way around, sorry. Actually, it would be easier just to change this.
Yeah.
So this would be depressed, and this would be potentiated. So if we look after a long time, then there will be a difference. There will be difference in the average. If we add more and more memory patterns, eventually we will revert to this distribution.
What is the F versus?
This would be the value. So these are the different possible values of a synapse. So this would correspond to the different states. So after depression, there will be no one at the highest value. Considering only those that were depressed, there will be no one at the highest value. Considering only those that were potentiated, there will be no one at the lowest value. And depending on the exact details and what we do with the bounds, then we'll have some change in the distribution here or here. Now, after adding a sufficient number of, with more and more memory patterns, eventually both these neurons, these synapses, and these synapses will eventually revert to this distribution. This is a stationary distribution. And the question that we ask ourselves is, how many patterns can we add before this and this will look exactly like this? So what's the answer? How many until it will look exactly like this? How many patterns do we need to add until this distribution looks exactly like this distribution?
You're getting closer, but you're actually getting there at some point.
So you're getting closer. So the answer is, how many patterns? Infinite. It will never converge exactly. It will get closer and closer. The distribution will converge exponentially fast, but still there will always be a difference. So what is a reasonable measure? What's a reasonable measure that we need to consider? So one reasonable measure would be to say the following. Let's look at all these neurons. All these synapses, or look at all these synapses. Now, as a population, when will we be able to say that this is different from this? When we look at the empirical values of the synapses, and they will be sufficiently different from this distribution such that we will be able to say that this is not this distribution. Put differently, a measure of when will we reach this point will depend on the signal, the value of the signal, how different this is from this initially, but also on the noise or the variance in this distribution. Or put more precisely, the difference between this distribution, this is like the theoretical distribution, and the empirical distribution, the real values of the neurons, because the real values of the synapses, because the number of synapses in the network is finite.
Can you repeat that?
Yeah. The number of synapses is finite. So if you look at the empirical distribution, it will never look like this. Maybe it will be slightly higher here and slightly lower here, because the number is finite. And this will change over time, even if there are no memory patterns. So memory will be lost when this will be as close to this, the empirical distribution of this will be as close to this, given the level of variability in the empirical distribution.
It's sort of like a t-test.
Yes, if you are a fan of a t-test, yes. Yes.
But why looking just at the mean? Maybe the empirical mean is the same, but the distribution is.
So maybe it's sufficient to look at the. Maybe you need to. Maybe looking at the mean is not the best thing to do. Maybe looking at the kurtosis or. Yes. It could be, but we will just look at the mean. Yes.
The top one is the beginning, or is it the end in which we can't add any more memory?
So the top is many things. Okay. The top is a stationary distribution, and at any point in time, every synapse is in a different state. Okay. There is one particular state, but looking at all synapses, they are distributed like this way. After a potentiation, after a presentation of particular memory patterns, some synapses will be potentiated, some will be depressed. We look at all those that were depressed, this is how they are distributed. We look at all these that were potentiated, this is how they look. But if we look at the entire network, it will always look like this, up to some fluctuations. Now, if we want to ask does not bearing in mind your concern, if we say, okay, I want to test the question of whether this set of synapses was potentiated and this was depressed and this was potentiated. So I'm looking at the average of these minus the average of this. If this is sufficiently different, sufficiently positive relative to just choosing randomly from this distribution some synapses and subtracting an equivalent number, again, randomly chosen, then I would say that there is still some memory in the network. So one thing that we will need to, if we think about it this way, a measure of when will it converge would be, first thing to compute would be what would be the variance. What would be the variance of this difference in the weight between those potentiated and those depressed. Okay? Are you with me?
There's one point I don't really.
I'm sorry?
There's one point I don't understand. You think that when the distribution is every synapse is in the same probability, every string of synapse, then the memory is forgotten. But so there's the same number of each weight.
Sorry, I did not understand your question.
When the bars are at the same height, it means that there's even probability for every synapse strength. That is possible, right?
Yes.
But so I don't understand why this means that the memory was forgotten.
So when all the ones that were depressed look exactly distribution of synapses, of values of synapses for all the ones that were depressed by a particular memory pattern is exactly equal to all those that were potentiated by a particular memory pattern, then I cannot say whether indeed these were potentiated, these were depressed, or that there was no memory at all. There was nothing. There was no ever potentiation or depression.
But it matters which synapses were depressed and
Exactly. I'm looking at, I'm taking the set of that ones that were depressed by a particular memory pattern and the ones that were potentiated by a particular memory pattern, and I look at the difference between them. Now, if they look exactly the same, as if there was no depression and potentiation, it means that memory was lost. Yes. Sorry.
They don't have to look exactly the same for the upper graph to be even.
The upper graph corresponds to the distribution, to the prior distribution before the potentiation and depression.
So it's not the summation of the...
It's also equal to the summation of the two, because we're in a stationary state.
Okay, so they don't have to be identical for the upper graph.
Let me write another line, and then I'll go back to your question. Okay? I will after this. Okay? So let's look at 1 over n. Yeah. I was hoping that this would be, just like. So let's look at this term. I want to address your question. Let's look at this term. This term is the average over all synapses, taking the ones that were potentiated minus the ones that were depressed. This is the measure that I'm considering. Okay? Now, immediately after the presentation of the memory pattern, this will be different from 0. This will be positive. The ones that were potentiated will be larger than the ones that were depressed. With the presentation of more and more patterns, the distribution of these will become more and more similar to the distribution of these, such that the difference will become smaller and smaller. At some point, the difference will be so small that it will be as if it will be equivalent to the difference if I just randomly choose some synapses and consider the difference between a subset of randomly chosen synapses and another subset of synapses. And if this difference is as small as, in fact, the variance of this distribution, then I cannot say whether indeed these were potentiated and these were depressed. So this is a measure, this is our measure that we will follow with the addition of more memory patterns. So what we care about is so let's assume now that we randomly choose from this distribution. Let's assume that we randomly choose from this distribution synapses and look at this measure. Okay? So now, rather than looking at those that were potentiated and those that were depressed, we're randomly choosing f times n synapses and call them potentiated, and f times n synapses that we call them depressed, and then we consider this difference. So we will consider the variance of a sum of n times f synapses that we will call potentiated and n times f synapses that we will call depressed. What will be the variance of this term? So what will be the variance of this term?
To open it up.
I forgot the 1 over n. So what we have here, well, we can take the 1 over n outside, so this will be 1 over n squared. And we have, how many terms do we have here? 2nf times the variance of the synapse. So if we just randomly choose a term. So this would be just proportional to f over n. If we think that the synapses are we just normalize them to be between 0 and 1. So we'll have the 2 term, and we'll have the variance of a uniform distribution, but these would be order 1 terms. So the requirement So if we think about this as the signal or something, so what we will require is that s of t over square root of f over n should be larger or much larger than 1. This would be the requirement. This would be the signal, this term, and this would be the noise. So if the signal over the noise is much larger than 1, then we are okay. So this signal will be asymptotically equal to S0, the initial signal, perhaps it will be more, to use the same notation that we used previously, I'm going to say the signal after presentation of p patterns. So this would be the signal after presentation of p pattern. So this would be approximately equal to the initial value times lambda to the power of p. Now lambda is equal to lambda is equal to f pi square over m square, 1 minus. So S of p will be approximately equal to S of 0, 1 minus f pi square over m square to the power of capital P. So what do we do with this? E to the p log 1 minus f pi square over m square. And since we are working in the regime where m is large, this will be equal, symptotically equal to e to the minus p f pi square over m square.
What, this is small, pi over m is small, right? That's
Because
what
m
you're
is
saying?
small, yeah.
So why aren't you Taylor extensioning it?
That's what I'm doing. I'm Taylor
No, of
extension.
the first term, just 1 minus p f.
Because p is large. P can be large.
Oh, like it's the first two terms of the exponent. Okay.
As it's not, you can't just take the linear term. It's not equal to 1 minus pf pi square over m square.
All this is because p is very.
Yes.
So you came up with this equation because of the dynamical equation?
Because of what we learned from the Markov chain.
Propagate with number of memory patterns or something?
Yes.
Yeah, we've already seen that it decays fast, and this is to show us what the decay depends on, or
Yeah. Well, this is something that we knew previously. Okay, I don't want to keep you, so let's take a break. And 5 minutes after the break, I'm going to finish and allow Itamar to continue. I see that people are tired and sorry. 5 minutes after the break, and we will be done. כן.
אוקיי, אז אמרנו שהשלב שלנו הוא כאילו יכתיב לנו קצב דעיכה קצב, כלומר זמן, אבל פה אתה מקדם את זה עוד זמן.
אתה יכול לחשוב על זמן time in units of pattern presentation.
מה חשיפה
כל שנייה יש עוד
כל שנייה יש תמונה חדשה. אם אין לך... לא, שוב, המרקוב אומר לך כל פעם שיש לך memory pattern חדש, אתה עושה שינוי.
אוקיי, אז עכשיו יש לי שאלה אחרת.
כן.
כשאתה אומר memory pattern embedded in Matrices, אני חושב שזה איזשהו אוסף של גופים שאנחנו בפשט ואנחנו פשוט עושים כל מיני דרישות בנוגע אליו, אבל כמובן שלא, משהו שאני מציג
גם בהופפילד זה היה. כל פעם אתה מציג תחילה. דיברנו על זה, שאתה יכול לחשוב על ההופפילד בצורה הזאת, שכל פעם דוגמה חדשה.
כל פעם אני מציג תמונה חדשה. אז אתה אומר, אוקיי, כאילו אנחנו מדברים על, אני חושף את רשת לפאטרן בכל פעם. זה כאילו שאמרנו שיש לנו פי גדול בכמה פאטרן, אז זה בעצם אומר שאני חושף בו זמנית לכמה memory patterns, או שאני פשוט אחד אחרי השני. כאילו, אני לא מצליח להבין.
יחידות הזמן זה יחידות של חשיפה.
כן, אבל נגיד כשדיברנו על הקפסיטי. כאילו, זה לא היה איזושהי מנגינה, דיברנו על ההפך.
אתה מסתכל מה קרה אחרי פי memory patterns.
עכשיו טיפה לפי שונים, זאת אומרת, אחד אחרי השני.
כן, פי שונים. עכשיו, במודל ההוא, מלך הבאונד, כל הזיכרונות תורמים בדיוק אותו דבר, לא חשוב אם היית מזמן או אם חדש. במובן הזה, האספקט הזמני הוא לא חשוב. ברגע שיש לך מודל כזה, אז האספקט הזמני נהיה חשוב בגלל הבאונד. באונד מכניסים אסימטריה בין פאטרן חדשים ופאטרן חדשים.
בדיוק. מעולה, וואי, אני בכלל לא הבנתי מה שקרה כאן שיעורים לפני. עכשיו אני עדיין לא חושב. תודה. כאילו נראה שבהקשר למה ששאלתי, אם זה מה היא יכולה להיות אופטימית לצייר, אבל לא נראה לי כאילו אין סיבה של נורמל, כן, בנפס משהו כזה נראה לי סדר גודל של חצי. הוא לא אומר שיש התפלגות סטציונרית. לא זוכר, זה תלויה במטריצת מעברים, תלויה בעמידה ובהנחה יש לי התפלגות סטציונרית ואז יש שתי התפלגויות כאילו אחרות שרוצים להבין מתי הן חוזרות להיות ההתפלגות הזאת.
לא אקספוננציאלי, זה דרך אחד. למדה פי. טוב, זה אקספוננציאלי, נכון, כי את רואה כי יש לך פי, כאילו, זה שם. כן,
אז כל פעם לחזור מיד גם.
לא, השאלה כמה מהר אקספוננציאלי זה דרך. יש לך אקספוננטים דועכים שדועכים לאורך 100 שנה, ואז אקספוננטים דועכים שדועכים תוך שנייה. אם מחזקת למינוס פי. לא, זה בדיוק מה שעכשיו מחפש, אתה יכול לדעת למהירות הזאת. איך המהירות הזאת תלויה ב-L שלך או ב-N. נראה לי שככל ש-N מגדל, ככל שתאפשרי יותר גדול, אז היא דף יותר לאט. אם זה מחזקת מינוס פי, אז מה זה, מתי נדע בחצי? אז זה תלוי ב-M בעצם, כאילו אם תבחרי את M טוב, אז תוכלי לקבל כאילו M שהוא מספיק גדול ביחס ל-P, אבל זה M בריבוע, אז כאילו התרוצה הרבה יותר גדול מ-P. קיצור, זה איזשהו מנהל מהירות של הדעיכה הזאת. ועכשיו זה נוגע למה שדיברנו על. מה השאלה? אני אגיד לך מה הפואנטה, אני אגיד לך. כשאנחנו דיברנו, את אמרתי שנכון, לפי אז הכי הרבה, כאילו כשיש לי מערכת N, אז הכי הרבה שאני יכול להכניס זה פי בריבוע. נכון? עבור שתי נוירונים 4. 2 בחזקת N. אז אני אומר, זה מדד שהוא לא רלוונטי, כי גם ככה מספר הזיכרונות שאנחנו יכולים לשים מוגבל על ידי N. נכון? N, לא על ידי P, לא בחזקת 2. לא, מוגבל על ידי N. זה העניין שמראש בשביל שהמערכת בכלל תעבוד, אז ה-2 בחזקת N, פשוט N. P לא יכול להיות גדול מ-N. מספר הזיכרונות לא יכול להיות גדול מ-N, כי אם מספר הזיכרונות גדול מ-N, המערכת קוראת. וזה עוד הרבה יותר גרוע.
היא גם לא יכולה קרוב ל-N.
הוא לא יכול להיות קרוב ל-N.
הוא להיות חזק בגלל שהוא לא יכול להיות...
הוא צריך להיות קטן מ-2 בחזקת N? ברור שזה חזק.
הוא לא יכול להיות גם שווה ל-N, הוא צריך להיות רחוק מ-N.
נכון, זה לא להיות לך. אני אומר, 2 בחזקת N הזה הוא לא מעניין. מספר הזיכרונות שאני יכול לייצר הוא לא גבול שמעניין אותי בכלל. כי הגבול שלי הוא הרבה מתחת. אז אני צריך להיות... אז אני רק רוצה לסיים. אז אני אומר, במערכת של N זה, מה שאני שזה, בסוף שאפילו מספר הזיכרונות, הקפסיטי של הזיכרונות שם, הוא אפילו לא N. הוא צריך להיות 0.1N, 0.01. נכון? כי אחרי זה קורה. נכון? מה שקורה במערכת שלנו, של הסוויצ'בורד הזה, זה שאנחנו לא צריכים 0.1N. אנחנו רוצים ש-N יהיה בערך, P יהיה שווה ל-N, P שאלפא יהיה שווה בערך 1, אז אלפא N יהיה שווה 1. כלומר, זה מגדיל לי את הפסיפסים בערך. אני רק צריך לדאוג שהשוואה עם זה תהיה נורא גדולה. כלומר, N צריך להיות מאוד מאוד גדול, אבל כל עוד יש לי N בסדר גודל של P, ו-N נורא גדול, אז הזיכרונות עוברים שם מצוין, בלי טעויות כמעט, עם טעות מאוד מאוד קטנה.
מה זה M גדול?
זה לא ממש.
מה?
מה זה M גדול?
לא אינטואיטיבי, פשוט לפי המשוואה, או מה שיוצא.
קשה לי כזה להבין מהמשוואות.
למה זה קורה? למה זה עובר בכל מקרה?
לא, כן, בגלל שהשכבה הקטנה היא מגבילה את השכבה האחרונה.
כן, השאלה אבל איך היא מגבילה, זה בדיוק השאלה איך היא מגבילה. האם היא מגבילה כ-0.1 השכבה הזאת, או האם היא מגבילה כ-0.9 השכבה הזאת? זה תלוי בגודל של השכבה האמצעית. כאילו, הגודל של השכבה האמצעית מאוד מאוד משפיע. אם ראית שהטעות בשכבה השלישית הוא תלוי מאוד חזק בטעות בשכבה השנייה. כלומר, אם יש טעות מאוד מאוד קטנה בשכבה השנייה, אז הטעות בשכבה השלישית היא גם תהיה מאוד מאוד קטנה. כאילו אם M נורא גדול, אז הטעות בשכבה השלישית, אם M מאוד גדול, אז הטעות בשכבה השלישית מאוד מאוד קטנה, לא משנה מה הפרופורמט של N. כאילו, כמעט תמיד בשכבה שלה אין טעויות. תהיה הרבה יותר קטנה. כן, בדיוק, זה העניין. השגיאה תהיה הרבה יותר קטנה. M מ-2 ל-3 היא הרבה יותר קטנה. איך זה קורה? זה קצת קשה לי לתת אינטואיציה. איך זה יכול להיות שכאילו למרות שיש לי שגיאה יחסית גדולה בשכבה השנייה שלי, השגיאה בשכבה השלישית קטנה? זה מה שקורה כאילו כשאני...
אבל אם רגע שנייה נחשוב על הקורס האינטואיטיבית, אתה מקבל
So little energy plus n is taken. So say the change right when we
אתה רוצה שאיזשהו output יוצא לך איזשהו input יוצא יותר
which are potentiated go up by 1 over the square root of the
נכון, זה איזשהו
every time. After that, instead of the potentiated go up by 1 over the square root of the
השאלה היא יותר שתהיה מבחינת היכולת של המערכת, מבחינת המים, כאילו השאלה אם זה נראה ביד משהו.
So each of those terms we have two
כאילו נראה לי מה שאתה אומר, יש כמה ששכבה אמצעית קטנה יותר, ככה שהשגיאה לשכבה השלישית גדול יותר.
כן, זה לא שאלה. השאלה היא שדווקא אין קטן, נראה לי המקרה הכי מעניין, כשיש לך שתי שכבות גדולות יחסית גדולות, יש שכבה אמצעית נורא גדולה. זה נראה לי
M גדול מהן?
שאין גדול מהן.
למה זה מעניין? כאילו, למה זה... מה אתה אומר? השכבה השלישית פחות או יותר מהשכבה הראשונה?
זה נותן לך פשוט יחסית מערכת עם capacity גדולה, אבל עם לא הרבה כל כך נוירונים, כי היא רק שכבה אחת גדולה, במקום 3 שכבות גדולות, או במקום מערכת N על N.
אבל רק בשכבה הראשונה אני שם את הזיכרונות. רק בשכבה הראשונה יש את הזיכרונות.
נכון, זה מגדיר לך את היכולת לשים שם.
אני לומד את זה.
לא, אתה לא יכול לעבור את N בלי קשר.
בשכבה הראשונה, נגיד אני יכול לשים אם יש לי 3 שכבות,
אתה יכול להתקרב נורא קרוב ל-N
זיכרונות
ועדיין לקבל תוצאות מאוד טובות.
לפי זיכרונות. לא, אתה מסתכל על הטעות בשכבה השלישית יותר קטנה מהטעות בשכבה הראשונה?
זה נורא קשה.
כן. בשכבה הראשונה אבל אין טעויות.
כשאני מקבל עם המשוואה, אני לא.
למה אני צריך את השכבות האלה? בשכבה הראשונה אין לי טעויות, נכון? זה השכבה המודלת.
אני אגיד לך מה למדנו לאורך השנים, לא אחוז נגידים שהאינטואיציה שווה לצד. ואתה צריך משוואה בשביל לקבל מה. לא, אתה צריך, אתה קודם, אתה לוקח הרבה זמן לבנות אינטואיציה בנוגע למשיכות כאלה, עד שאתה לא ראית אותם מיליון פעם.
חצי שנה אחרי הקורס מגיע.
יש מלא דברים נוגדי אינטואיציה, יש המון דברים נוגדי אינטואיציה.
אינטואיציה זה אוברייטד.
מה, בחיים?
אינטואיציה זה דבר נרכש.
לא, אני לא אומר פה, אני לא יודע הכל ספציפית, פשוט ככל שמערכות הולכות ומתפתחות, ככל שהן פחות ופחות אובייס מה קורה בהן, כמו הפיטבורד או הסינאפס, או זה שאתה מתחיל לבנות מערכות שכבות וזה, אז האינטואיציה מתחילה להיעלם לפני שכאילו אתה לא ממש יכול לחשוב מה, לא יודע, יכול להיות מה, איך תשפיע הגדלה של N והגדלה של N? אינטואיטיבי? מה האינטואיציה שלך פה נוגע לזה? ששינוי היחס ביניהם לבין מה? כן, כאילו איך שינוי ביחס ביניהם לבין משפיע על היכולת של המערכת. אני בטוח שאפשר, אבל כאילו כל עוד אנחנו לא מסוגלים, אז אני כאילו פשוט הולך למשפט ושואל. שארים אין על אין. מה זה? זה כאילו, זה קצת מערכות שעושות דברים שונים, אז זה קצת מצחיק. מה שונה אין תיאוריה? סתם בעין. אתה יכול בעזרת שכבה, נגיד, אתה אומר עם שתי שכבות ומה שלוש שכבות? מה זה שכבה אחת? שכבה אחת זה לא כלום.
לא, זה מה שאנחנו פתרת עד היום.
לא, זה לא שכבה, האופק זה לא שכבה, האופק זה אין על אין, זה כולם על כולם. זה אין על אין אירוני.
שכל אחד מדבר עם השני באיזשהו...
כן, אני מתכוון מבחינת הקולקטיבית. כאילו כמה סינפסים.
לא,
איך אומרים את זה? סינפסות? סינפסות?
אני לא מכיר את הז'רגון.
השאלה כמה סינפסות? יש לך אין על אין סינפסות? מה? אני יכול אתה רוצה גם אינטואיציה. אני אחשוב כי כאילו יש לי שגיאה בשכבה גדולה. יש לי בעיה כאילו מה גדולה, השגיאה
Okay.
זה מאוד מאוד
We're at a turtle's pace, but still we have to continue. So the signal will decay exponentially with the number of patterns, and the requirement is that this signal divided by the standard deviation of the stationary distribution, which is proportional to this term, up to some, so there will be 2, and there will be, here there will be 2 and 1 over 12, because it's a uniform distribution, but we don't care about these added constants. Then this term has to be larger than, much larger than 1. If this is be smaller than 1, then it means that the signal is lost at the level of the population. And we can rewrite this as p has to be smaller than m squared over pi squared f, the logarithm of s0 divided by square root of f over n. This would be the requirement. So we can just rewrite it. Okay, let's stop here for the time being. So we have this prefactor of m squared divided by pi squared f, and the number of neurons in the network, or the number of synapses in the network, appears here. Okay? This is just rewriting this term. So if we think about f that is order, well, in the Hopfield case, what's f? Half. So let's say that f is 1/2. Then here we will have 2 m squared over pi squared. That's fine. Well, s0 will be in order 1 term. So this will be in order 1 term.
S0 is the first difference?
Yes, the initial difference.
Initial difference is not like 1 over n or something?
No, because we have sum over n terms in principle.
Different from what?
Oh.
The difference, the average difference in the values of the synapses potentiated minus those that were depressed. Immediately after the presentation of this particular memory pattern. So here, let's say that, so this will be on the order of, the number of potentiated will be on the order of f times n. The number of depressed will be on the order of f times n. And the change in potentiation will be on the order of 1 over m. So you have f over m with a factor of 2, 2f over m. This would be the magnitude of the signal. But here I'm cheating a little bit. Why am I cheating? Why am I cheating?
I have the feeling that what's going on.
Looking at my eyes, you say, he must be cheating. It's like playing poker. He's bluffing. This is not 2, it's 3, right? Well, the reason that the place where I'm cheating is the fact that the signal and the noise, in fact, this is not the value that we need to look at. Rather, it is a projection on the eigenvector that corresponds to this eigenvalue. This is where I'm cheating. So actually, what we're interested in is not the signal, this signal, but the projection of this signal on the eigenvector that corresponds to the subdominant eigenvalue. But if f is order 1, m is order 1, then they will be of the same order of magnitude. Then we're okay. So if m is order 1 and f is order 1, then this term will be very small, and the capacity will be dominated by this term. So this would be for m and f are order 1. Order 1 can be 100. Order 1 for f can be, I don't know, 0.1, 0.01. Then the capacity will be p smaller than m squared divided by pi squared over f times half log n. What is n? Small n. N is the number of synapses. In a fully connected network, n is equal to n squared, number of neurons squared, which will be equal to m squared pi squared f times log n, where n is the number of neurons in the network, large n. Now these are horrible, horrible news for you. Because previously you thought that you are able to store order n memory patterns with your 86 billion neurons that you are so proud of. But now, I have to break the news to you that you can only store log n number of patterns, which is a much smaller number. Much, much smaller number.
9.
And the only reason is that your synapses are bounded and have a finite number of states. Choose very carefully what to learn and remember, my friends. You don't have, your capacity to store memories is not very large. So what seemed to be not very important change to the model, the fact that we added bounds, or that we bounded the synapses, or required a finite number of states, the consequences are horrific. Really. We moved from n capacity to log n capacity. So I can't remember who it was on Sunday somebody asked me immediately, okay, let's take small f. You said. And I said, oh, I didn't want to talk about it. I still don't want to talk about it, but it's a good point. So, what's your name? Idan. So Idan said, okay, we don't care about all these calculations. Let's go back to the eigenvector, to the eigenvalue. Idan said, look, we have this f times s term. Let's take a very small f. Well, let's say f is equal to 0. I was mocking him. And if f is equal to 0, well, it sounds like a good idea because there will be no decay. But sure, there will be no decay, but there will also be no signal. So the signal will depend on f. So the signal, if we take very small f, then this will become very small, the signal. So we have an issue here that we need to worry about. Maybe we gain here, but we lose here. We cannot take f to be equal to 0. F can be very small. So it turns out that if you take f to be, you scale f with the size of the network, you can gain and reach capacity which is order square root of the number of neurons, which is a big improvement over log n, but still it's a much smaller number than n, square root of n. But in order to see it, this is kind of complicated because then now we need to talk about the eigenvectors and really look at the projection on the eigenvector. Things are more complicated, but it turns out that you can reach a capacity which is square root of n. So we have an issue here. There are many issues here. One issue is a requirement for fine-tuning. The fact that f plus has to be equal to f minus. We saw it in the Hopfield model, but we also see it in this analysis. F plus has to be equal to f minus. So in order to store memories, we need a large, we need balancing the potentiation and depression associated with the different memories. That's a substantial concern. Another thing is that we need that the probability of change will be rather the probability of change in response to a memory pattern will be rather small for every synapse. Otherwise, we have the capacity is only logarithmic in n, which is an issue. The question of how can we store memories with a small number of with a reasonable number of states is something that people are still working on, still meaning the last, 5 years or so. Larry Abbott made that wrote a paper, one of the co-authors of a paper that I was discussing. Part of it will be here in the Gatsby meeting 2 weeks from now, but he will talk about something else, I think. Some idea that people have proposed is that synapses have internal states, and with the right construction of internal states, you can retrieve the order n capacity without an order, with bounded synapses and bounded states, but it requires some fine-tuning, and so this is an issue which is still under investigation. Yes.
So the whole point of this framework is just to limit the number of synaptic states to make it more flexible. That's the motivation?
The motivation was to study what are the, well, for me there were two motivations. First, I wanted to teach you a little bit Markov chains, which are a useful tool in computational neuroscience. That was one motivation, the mathematical tool. But the second motivation, the motivation underlying this analysis, was to say that the Hopfield model is not biological. And it's not biological not because we use hyperbolic tangent or something like this. It's not biological because we assume an infinite number of internal states. And if we limit the number of internal states, then the qualitative behavior of the model is completely different. So we need to worry about it if we think about these kinds of models as models of memory. More questions? So many hours too late. I'll pass the microphone to Itamar.
I was ready to start this on Sunday.
Yeah.
Second hour. Okay. I hope you enjoyed that whole new topic. It was a new topic. If you look for the previous notes, you won't find anything about it, and probably won't find anything about it in textbooks or anything like that. So, first try at this topic. Okay, now we're gonna switch gears. We're gonna get ready to switch gears completely and leave Hopfield and memory behind. And in order to do that today, we'll transition from Hopfield to random matrices. And I'd say random matrices not in the sense of stochastic matrices that Jonathan presented, which in the Markov chain we have matrices that define a random process. Here we'll be talking about matrices that are themselves random variables. And I'll say exactly what I mean. So. Okay, so for a second we'll go back to our original basic Hopfield model. We have, of course, dynamics. And crucially, we have this matrix, which, as we've already noted a few times, that itself already, this matrix is a random matrix. Jij is random. It's fixed according to, of course, our memory patterns. Pi mu, pj mu equals 1 over n, where each pi is, of course, plus or minus, we'll go back to the original case, plus or minus 1, with probability 1/2. Okay, so as we've mentioned also a number of times, in the large n limit, Jij, we can look at Jij as a random variable. What's its distribution? Normal, right? It's effectively binomial. It becomes normal in the large n limit, and it has mean, of course, 0, and it has variance. Anybody know stuff that has variance? We'll leave it. It's going to be an exercise for you guys to calculate the variance, but we can calculate the variance of Jij as a function of p's in a p.
Yeah.
So I'll leave it for an exercise, but we'll calculate the variance sigma squared as a function of p and n. Right, so that'll be an exercise. And then in the large n limit, Jij is distributed normally with 0, sigma squared, p as a function of n, some variance with some scaling with n. You'll see what it is. So now I want to ask the question, maybe we don't need memory patterns at all. Maybe we have these things as a random matrix. We're building a random matrix here. We have the distribution. What will happen if I just say, I can't be bothered with memory patterns. Let me build a random matrix with the identical statistics to the Hopfield model. Right? So we'll call it Hopfield-like, but we'll just define it according to this distribution. So what if I just build it that way? Jij, call this old one, this is Jij Hopfield. And we're going to now build a Jij, which is just normally distributed, 0, and with the same sigma. What? I can compare P and N. I could set a scaling of P relative to N, whatever I want, as in the Hopfield. But now I'm just going to build Jij totally at random. What's going to happen and how is it going to compare to the Hopfield model? That's our question. That's our initial motivation to transition into talking about random matrices.
So what is the difference? How can we see the difference? So it's not based on the memories?
Right. So that's a good question. How can we see the difference? And that's what we're going to ask. But explicitly, there are no memories in this version. I just say I take Jij and I draw it at random from this Gaussian distribution. Right? So what are the differences? So what do you guys think?
There's no memory.
Okay, there's no memories, but maybe there are fixed points.
There are 6 points.
Maybe there are fixed points, so maybe those turn out to be memories. What's the problem? I have a fixed
Random
point.
memories.
Okay, these memories were random anyway, so maybe I can just build this. It'll turn out to have memories. I can find what those are, say, and then I can say, okay, now I have a memory. I can use that as a memory, maybe, right? Maybe. Maybe there's no reason to do this to be first. So what?
Maybe those 6 points won't be necessarily correlated with the patterns themselves, but if we take like a very large matrix, we have like a bigger probability to have the 6 point, which is the memory pattern. Maybe.
So remember, to begin with, these memory patterns don't have any information, anything interesting in their structure, and in fact, they're especially useful. They work very well when they're random, right? They're not carrying explicit information. We have to have some additional thing that matches between like apple and a particular memory pattern and carrot and a different memory pattern. So it sort of maybe doesn't matter. Maybe I'll just see. I'll get fixed points here, and I'll say this fixed point's apple, this fixed point's carrot, somehow in some kind of way, which is not but maybe not. Yeah.
But are you able to trace back from J what was N? What was the memory?
What was the memory pattern? So in this case it'll be harder, but let's say maybe we can do it. But so what are the differences between this matrix, between this new Jij and Jjh? Yeah.
Can you build any matrix using this sum? I mean, can you get any matrix at all?
Can you get to any matrix from this sum? That's an interesting question.
Maybe it's not symmetric.
Okay. The very first thing to say, okay, if I just take every single Jij at random, so then there's no reason to say Jij is equal to Jji. And then we may not even have any fixed points at all, right? We used, importantly, the symmetry in Hopfield to build an energy function. We know that a symmetric matrix guarantees that we have an energy function, and therefore guarantees that we can have fixed points. If Jij is not symmetric, maybe there won't be any fixed points. So that's the first thing.
Build a symmetric J.
So let's build a symmetric one. Let's do that, exactly. So let's require that Jij equals Jji. So effectively we can say we're going to draw the Jij, the upper triangle of the matrix from this random distribution, and then set the elements below the diagonal to be just equal to the upper one. So you'll do that in the exercise.
Is the diagonal 0 or like?
Yeah, let's say the diagonal is 0, like in the Hopfield case. Okay, so that's the first thing. It's important. So now we've done that. Say Jij is equal to Jji. We have symmetry. We've guaranteed 6 points. Okay. What else? Now the statistics of the marginal statistics of Jij are identical. That's how we built it. But are the matrices effectively the same?
You don't have control over how many.
What? How many what?
How many fixed points?
We don't know yet about the number of fixed points. Yeah.
So before n, you had some normalization to 1 over n. So maybe here we also need to somehow normalize.
The normalization is an interesting thing, but effectively it comes out in the variance. The 1 over n contributes to the scaling of the variance, and so that we're including. Yeah?
Did you say anything about the number of fixed points in the previous item?
We talked about specific fixed points that we were interested in, right? The memory patterns themselves are fixed points, but then there's all these other fixed points that are mixed ones. Right. I think it turns out even here maybe the number of fixed points might be exponential in P. As we add more memories, we have like all kinds of different mixtures of them in the Hopfield case, and maybe we'll see something similar here. Yeah.
In the Hopfield model, the Jij is discrete after all. No? Continuous like that.
Okay, it's discrete, but in the large n limit, those gaps 1 over n become effectively continuous. That's not going to play a crucial role.
Bounded, but I'm not sure if it's interesting.
It's what? It's bounded in the sense of P from... Yeah, okay, right. If we have like a finite P, then we only have kind of a finite sense. But that's not the crucial thing. What's the most important thing about matrices?
Size.
Hmm?
Eigenvalues.
Eigenvalues. Yes. Okay. So what are the eigenvalues of the Hopfield? Okay. Let me write the Hopfield matrix in matrix notation, matrix and vector notation. So same thing, 1 over n, sum over the memory patterns. But this pi, pj, effectively that's an outer product of the vectors, the entire vector, p mu transpose, right? Okay. I can say here I'll add eigenvalues, but also rank, the rank of the matrix. Okay? What's the rank of the Hopfield matrix?
Probably full.
Probably full.
If
If
n is large.
n is large, it's full. That's a guess.
If they are independent, the memory is
Yeah. We'll assume they're independent. We'll take them at random, so assume that they're independent. Okay, so we have p independent vectors. Okay. How many vectors do I have? So I have, let's call it I don't know what. Call it say SP, that's the span of these vectors of all my memory patterns. From mu equals 1 to p. What's the dimension of the orthogonal complement? That is, how many vectors are there that are linearly independent and orthogonal, or independent of this span, not in this span? N minus p. P orthogonal vector in a space n minus p. I want to deal with the notation. Dimension n minus p. Right? I can take n minus p different linearly independent vectors that are orthogonal to here. So what if I take one of those vectors and I take j times one of these guys? 0. Right? Take a vector that's orthogonal to all the memory patterns, and there are n minus p of those. I get 0. So what's the dimension of the kernel of J? How many vectors linearly independent get mapped to 0 by the Hopfield matrix? N minus p. So the rank of the Hopfield matrix, therefore, the rank of the Hopfield matrix is p. Now, the truth is, one should spot this immediately from this formulation. So, one of the basic ways to formulate any matrix is as a sum of outer products. Any matrix can be represented as a sum of outer products. That's an important thing we won't go into here, but it's called the singular value decomposition. And any matrix can be written as a sum of outer products of different vectors. Usually, they're not always the same thing. That's a particular form, symmetric. And the number of those outer products that are not without a 0 coefficient is the rank of the matrix. And it's exactly for the reason that we've seen here, because we have a subspace orthogonal to the span that's effectively the kernel of the matrix, and its dimension is n minus p. So the rank is p. So that's the first thing to notice. The rank of the Hopfield matrix is p. Whereas if we build a matrix randomly with probability 1, we'll have a full rank matrix. Meaning the probability that by chance we pull up these JIJs that happen to be aligned in such a way that there is a non-trivial kernel is effectively 0 as n goes to infinity. Or even for small n, I think. But yeah, even for small n, that's true.
Why would these numbers be necessarily independent?
The memories themselves. So the rank maybe could be even smaller, but we choose the memories randomly.
Yes, to define a vector in my chance.
You can, but again, the probability will be 0 for n. Now that does depend on n. So we have vectors of length n, and we say randomly I'll just choose one, and it'll happen to be fully aligned. So it depends. All the n elements kind of have to be aligned. So it winds up being, we'll get into the details of it, winds up being that for large n, the probability that two random vectors are aligned is 0. So we build and we choose them in that way. We can do something better. You can have fixes to Hopfield, by the way, where you kind of explicitly choose vectors that are fully orthogonal and not just almost orthogonal, like our memory patterns here. But anyway, we have with probability 1 linearly independent vectors, and so the rank is p, but the rank is only p. Whereas if we try to build this random, even symmetric matrix, Jij, it'll have rank m, with probability 1. So J, the new one, rank J equals n with probability approaching 1. Again, I'm not proving that, but that's the first thing. Okay, so that's already a major difference between our matrices. What about the eigenvalues? So what are the eigenvectors of this matrix?
All memory.
So the first intuition is that it's going to be the memory patterns themselves, right? So let's see. We take J Hopfield times some memory pattern, let's say P1. What do we have? 1 over n. Now, I'll take P1 from the sum here aside, like we're kind of used to doing. P1, and then we have effectively the dot product of P1 on itself, plus all the other memory patterns. Mu not equal to 1, P mu, and then the overlap, right? 1 over n, the overlap term, P mu, dot product with P1. Overlap of the memories themselves in the structural component, right? So this dot product is 1, the same vector, they're all plus or minus 1, or sorry, n, so 1 over n times this is 1. So this is P1. Okay, so that's great. If we only had one memory pattern, then JP1 would equal P1, and P1 would really be an eigenvector. But we have all these additional terms, right? Where they have contributions from in the other vector directions. And the strength of those contributions is this overlap term between the different vectors. And so this is what I was saying. Now, because we chose them at random, though, this will be small. That's what was useful for us in Hopfield, in the memories themselves being stable fixed points, and that also has to do with kind of approximating at least the eigenvectors. So this whole term will be small. We've basically calculated it before. It's going to be order 1 over square root of n, each single one of these. And so long as p, so for finite p, this term is small. So at least for finite p, we can say that the memory patterns are close to being eigenvectors. They're not exactly eigenvectors, and for large p proportional to n, forget about it. But at least for small p, relatively, the eigenvectors are close to the memory patterns. And it turns out, again, I'm not going to prove it here, it turns out that the fact that the eigenvectors are close, these are close to the eigenvectors, so the eigenvalues are also going to be close to what we would have kind of in the pure single memory place. The eigenvalues are close to 1.
Can you explain why again?
So this whole term that comes from the sum is p. It depends on the sum over 1 to p, but if the number of memory patterns is small, then this whole term is a small contribution. So I almost have what I want as an eigenvector relationship with an eigenvalue of 1. but not exactly.
And what determines what contribution is that?
The size of P. If we take P very large, then it's already different, but at least for finite P, I'll just say that the eigenvalues are somewhere around 1. And for sure, they're order 1 with n. Okay. So that's important. Now, what about our random matrix? So this gets us into the theory. There's a whole theory and a whole field studying the theory of random matrices, and in particular the eigenvalues of random matrices. And that's something that we're not going to get to in detail in this course at all, but we'll just quote some results. It's a fascinating theory, and the mathematical techniques of how to calculate these are super elaborate. But we're going to suffice ourselves with just quoting results. So the result is called, it goes by the name of Wieners semicircle law. Here I'm going to quote the result for this distribution. When I say random matrix, I mean more broadly that Jij is taken from is a random variable. The theory of random matrices is broader than that. This result, I'll quote it, right? So the result is for a J exactly as we've defined it. Let J be symmetric with Jij given by a variance. Now here there's a scaling in the theorem, in the law, in Wieners semicircle law. There's some constant, allowed some order 1 constant, and the scaling of the variance is 1 over n. Okay, that's an important thing to pay attention to. So let J be a symmetric matrix with this normal distribution around 0 and variance given by g squared over n. Then, as n goes to infinity, now the eigenvalues themselves are random variables. So we can write a probability distribution essentially, but it turns out a probability distribution is also the distribution over the set of eigenvalues for a given matrix. That's kind of a subtle and weird thing. So we can think about the eigenvalues as a random variable where each time I build a matrix, I get a new eigenvalue. But it turns out that that probability distribution will be identical to the distribution when I just take a single matrix and I look at the distribution of eigenvalues of that matrix. So it turns out that as n goes to infinity, the probability density function of the eigenvalues, f of lambda, goes to a semicircle. Semicircle, I'll draw it in a second, between minus 2g and 2g. So it looks something like this. We have this density function on lambdas. And I should say, specifically, it goes to this semicircle between the values of minus 2g and 2g, and it's 0 elsewhere. 2g and minus 2g, and then we have this exact form of a semicircle. It's literally a half circle. And this is the density, the probability density function. So if I draw a new random matrix and a new random matrix, and each time I just look at some random eigenvalue, I'll find that most of them, the highest probability is that it's near 0. It has some distribution out to a maximum value of 2g. Minimum value of minus 2g, and out here, 0. In the large n limit, 0 probability of any other eigenvalues. That's the distribution. And like I said, in this subtle thing, it turns out to be equivalent if I just make one random matrix not repetitions on it, and I look at all its eigenvalues, they will fill up this semicircle. You'll see that numerically in the exercise. And so again, that's a result that is way beyond our level to prove, but it is very, very useful to us. In particular, it's useful to us because it will turn out, and this will also be part of the exercise, the Hopfield. So we'll write in the Hopfield variance that you guys will calculate, sigma squared as a function of p and n. When we write it as g squared over n, so now you guys will calculate what this function g needs to be. It's going to be some function of p and n. So you guys will calculate this in the exercise. You'll calculate what is the variance of the Hopfield matrix, and then you'll put it in terms of, you basically multiply it by n to find g squared and then g. What you'll see is that for finite p, g is very, very small. G is much smaller than 1 for finite p. So what does that tell us about the eigenvalues of this random matrix? We thought maybe we'll build a symmetric random matrix and kind of get something identical to Hopfield-like fixed points in dynamics and so on. What does it tell us about the eigenvalues of this symmetric matrix? So we build this symmetric matrix with the identical variance, sigma squared, and it's going to turn out, and you'll see it, again, you'll see it in the exercise, you guys will calculate it. It will turn out that this g is much smaller than 1 for any finite p, right? Meaning that the maximum eigenvalue, which is equal to 2g, for all finite values of p, the maximum eigenvalue is much, much smaller than 1. They'll all be very close to 0, right? Which is very different than the Hopfield. In Hopfield, for finite p, the eigenvalues, and it's even better, the smaller p is, the closer the eigenvalues really are to 1. Some number of them, right? The number of eigenvalues that are equal to 1 will be equal to p for finite p, and they'll all be equal to 1. For the random matrix, we don't have any eigenvalues near 1. They're all clustered very close to 0. Why is that? Why is that important? For example?
Weak stable.
Yeah, for the stability, right? The first thing we might think about, the eigenvalues of the matrix immediately will give us the stability condition on, in particular, the 0 fixed point. So that's the first thing, and that's the first thing we looked at in Hopfield, I think. We said, okay, there's a 0 fixed point where everything's just 0 and there's no memory. And what's the stability of that fixed point, right? What was the result there in Hopfield? What? When is it stable? When beta is smaller than 1, the 0 fixed point in Hopfield is stable. When beta is larger than 1, we immediately break the stability of the 0 fixed point, and we essentially get to the fixed point that we want, right? We showed then that we get to a fixed point that has some significant overlap with the memory pattern, right? For beta equals 1, and we found that independent of p. It didn't matter, and of course it didn't help us to add more p's, and when p was small it was great. We break the stability of the 0 fixed point, and we have some memory pattern immediately when beta equals 1. What we'll see here, and you guys will see it in the exercise, we're out of time, but what we'll see here is if we build this Hopfield-like symmetric matrix, the eigenvalues are very, very small, and so for any finite p, the fixed point is essentially, the fixed point of 0 is stable, as long as beta, for a order 1 beta. For finite p and for finite beta, we'll see that the fixed point at 0 will always be stable for this symmetric matrix. So at least, so we won't see the emergence of fixed points just for beta equals 1. So that's a significant difference between the symmetric matrices. Yeah, we'll have to drive the system and increase the gain to much stronger forms to get any interesting fixed points at all, or and or make P essentially very large. Yeah. So that's it. We'll continue along this path of random matrices with maybe a detour into statistical mechanics and eventually chaos.